Okay. So, good evening. We continue from last week. And there's another chapter that I want to talk about, which is motion planning for legged locomotion for robots with legs. How to plan the motion of the leg, how to conduct steps forward, and this is this section, and this will conclude the part of the motion planning, and we'll continue to dynamics. And so this is an in a general presentation. So a robot is the intelligent link that connects perception to action, and robots are used for dangerous, dull, dirty, and distance tasks. Locomotion. The definition of locomotion is the act of moving from one place to another. Locomotion relies on physical interaction with the environment to generate force, moving force. Locomotion is concerned with the interaction forces along with the mechanisms and actuators that generates them. In general, locomotion involves localization, then motion planning and control, and then the real robot, and the perception of what there is in the real world. Some issues of locomotion. First, for walking robot is the stability, maintaining stability, and there are several definitions of stability. Stability is a dynamic effect. Usually when we talk about walking robots, we talk about equilibrium, not stability, which is a static effect. And stability means that if a body is in equilibrium and you move it a little bit, it will stay there or move back to the equilibrium. And for stability, we need to know the number of contact points with the environment, the center of gravity of the robot. We talked about static versus dynamic stabilization. Well, static stability is actually equilibrium, it's not stability. And the angle of the terrain, the inclination of the terrain, and the structure of the terrain that we walk on. And this is important. The contact, so the contact can be either a point contact or a contact area, where an area of the leg touches the environment. There's the angle of contact, so the angle of the force relative to the normal of the contact, and the friction at the contact. And friction is very important. It helps us to move. Actually, when driving on flat surface or even walking on the floor on a horizontal surface, the only force that drives us forward, that moves us forward, is the friction. And therefore, it's very important to understand and to know how to calculate it and how to model it. The environment itself is also important, the structure, the medium, and the friction. In the nature, there are several types of locomotion. It can be like inchworm, or like sliding, like or even moving in a kind of a wave, a traveling wave like a snake, or walking and running and so on. As you can see here, for on animals with 2, 4, or 6 and 8 legs. That's what we have in nature. Why it's not working? Yeah. Okay. Many locomotion concepts are inspired by nature. Most natural locomotion concepts are difficult to imitate technically. Rolling, which is not found in nature, is most efficient because there is no loss of energy. And it's the fastest one. So the motivation for legged and versus wheel locomotion. Wheels are most suitable for high velocities. You can roll on the ground. Legs are suitable to overcome obstacles and climb stairs. Legged robots. So the advantage of legged robots is that they can traverse any terrain that a human or an animal can walk on. The disadvantage is the large number of degrees of freedom. It's very complicated to control it and to plan the motion. And maintaining stability is also complicated. Our center of gravity is relatively high. The contact area is relatively small, and it's difficult to maintain a balance. Walking versus rolling. You can see here types of, in the graph, the speed versus the power that is required in order to move. So, where's my mouse? There's the structural complexity, the control expenses, how much effort I have to put in order to move, the energy efficiency, sometimes it is called the cost of travel, something like that. Number of actuators. Is it, what is the kind of terrain? Is it flat, soft, or climbing? So walking on sand is very difficult. It takes a lot more energy than walking on a stiff surface. Movement of the involved masses, which mass is moving, whether there is a lot of mass at the end of the leg, like heavy shoes. This takes a lot of much more energy to move them. Walking, running includes up and down movement of the center of gravity. So when we are walking, the center of gravity is doing something like oscillating motion, and we need to take it up and down. So there's converting energy from a potential energy to kinetic energy, and there are losses in this transition as well. And some examples of walking. Here is not really walking, is climbing robot. on the left is from Urbana-Champaign. This is from about more than 20 years ago. And this is from here. We built in my lab a walking robot that can climb on walls, as you can see here. And it selects the footpad location in order to maintain balance and advance itself. Another model for locomotion of human-like humanoids, is the sleep model. It can have like a mass with a spring and damper, and does some kind of oscillating motion.
You just come across down this way.
This is a special snake-like robot that moves on the surface by
Good, right through the middle.
changing its body shape.
Wow, that one looks so smooth though. Looks really great on video. Yeah, it's
Here's another example of robots that are dancing. I think I'll show it already.
oh my god.
I try to skip on. It's nice, but the idea is to maintain balance. So mobile robots with legs, legged robots. The fewer the legs, the more complicated becomes the locomotion, especially the stability. We need at least 3 contacts, 3 legs that will be in contact with the ground to maintain equilibrium. So they can walk even if it's not in equilibrium, but in order to stand, at least 3 legs has to touch the ground. During walking, some legs are lifted, and this may cause losing stability or balance. For quasi-static walking, at least 6 legs are required, so 2 triples of legs that each time change the role in order to walk.
And what is static walking?
It's quasi-static. It's not static. It's quasi-static. It means that you can scale down the time, the time axis, and it will still work. So even if you'll do it slow, very slow, it will work. We are walking in dynamical manner, so we kind of fall forward, and this is kind of dynamic effect, and then put our leg in front. But quasi-static locomotion is when in order to move the leg forward, I need to take my body backward in order to maintain my center of gravity above the leg that is touching the ground. Okay? Yeah. Some design considerations. Small is easy. If the robot falls, it's not that terrible, and the motors are small, and the torques are small. Big is hard, so having a full-scale humanoid is difficult. There are many little robot kits. Designing a six-legged walker is challenging and pays off. If you take six legs, the control is much easier. Designing a four-legged robot walker is hard, but can be done. Designing a two-legged robot is very difficult because of maintaining stability. The minimum thing that we need is that all joints will be actuated, and we can control the leg to put it in any place that we want. There are examples here of several robots. The number of joints. In order to move the leg forward, we need to lift it and then move it forward. This is at least 2 degrees of freedom for each leg. But in most cases, we want to be able to maneuver, to turn, and therefore we want to be able to select the position where we put the leg on the ground. And for that, we need at least 3 degrees of freedom. Sometimes we add the ankle joint. It has effect also on stability, because then we can have a flat surface that touch the ground. And this will be the 4th degrees of freedom for the legs. But more degrees of freedom is more complexity. Here's an example of a spider-like robot design. So there is a trade-off between complexity and stability. If we want more stability, sometimes we'll need more degrees of freedom. And the degrees of freedom per system, too many needed gated motion. Gate is the pattern, how the contact points are moving, how the legs are moving. So we may have a constant gait pattern in which the robot will move according to a predefined motion, or we may want to adapt to the terrain, to the surface, and then and we need to control all the degrees of freedom. So balance, stability, equilibrium, static stability, all are the same name, the different names to the same phenomenon that we want the robot to be kind of stable. The first approach is the support polygon. I'll talk about it. We'll talk about dynamic and static stability and about the sleep model, the spring loaded inverted pendulum model. And then a little bit about gait pattern. Support polygon. If the robot touch the environment in several contact points, I draw the polygon between the contact points, and the center of mass must be above this in order to maintain stability. If the center of mass will be outside this polygon, then the robot will fall, will tip over. Center of pressure is kind of similar. So if I take the reaction force from all the legs and I combine them to a single force in a single position, then this force, this position is the center of pressure, and the center of pressure also has to be inside the support polygon. In equilibrium, the projection of the center of mass of the robot must be above the support polygon. And as you can see here, I lost my mouse here again. You can see here, this is leg 1, this is leg 2 of the robot, and the support polygon is the polygon, is the convex hull actually of the shape, is the polygon that combine all this shape, and the center of mass must be above this polygon in order to maintain a balance. This is from top view and this is from side view. You see that the support polygon is actually all this area and the center of mass must be above it. Sometimes for dynamic effects, some researchers like to see the human body while walking as the sleep model, the spring-loaded inverted pendulum, as you can see here. This is actually the center of mass of the body, this is the leg, and this is the contact point. And when we walk and swing on one leg, this is the kind of motion that the body is doing in order to move forward. So this is kind of a dynamic model of walking. About gaits, gait pattern. Gait is the repetitive sequence of leg movement to allow locomotion. So this is a certain pattern of motion. The gait is characterized by the sequence of lift and release events of individual legs. And you can see here several gait patterns of a four-legged robot. And you can see the legs that are lifted and legs which are on the ground and the motion as well. And sometimes we describe their motion in a diagram. As you can see here, this is the percentage of the walking cycle. The black is the leg that is on the ground, that is touching the ground. And you see here 4 legs left, left front, rear front, right front, and left back and right back. Legs. You can see for different type of patterns of motion. And this is their and this is for 6 legs. So it's a little different. So this is a gait where 3 legs are touching the ground and 3 are in the air, and then they change. Here are some examples of walking in. Not working? walking in a predefined gate, but with changing some parameters like the phase in order to overcome obstacles. This is not a movie, no. CPG is the central pattern generator that animals and also humans have in their spine, not in their brain, and generates the repetitive motion of the gait pattern. Here is a bigger this is the company that was built by DG, and here's this for using the field. Yes.
Why is it so slow? What are the limitations that are causing it to be so slow?
It's a good question. Basically, the control of the motors to precisely synchronize all the motor.
So it's a computational problem.
It's not the computation now is not the bottleneck, but the movement itself and synchronizing all the axes together is difficult to do when you're doing this fast. It's not impossible, but it's more difficult. And therefore, most walking robots are relatively slow. But you can see now Boston Dynamics have very fast robot.
But you can put wheels
Yes.
under the legs, and they can move fast when you want to use the wheels, and when
And
you
stop the wheel when you
when you
want to-
do obstacles.
Yes.
Yeah.
Yes. So you can combine. You see, this is another humanoid robot. Example from about 10 years ago. This was the DARPA Robotics Challenge. This is a simulation, but still,
Really?
yeah, it was real. This is a simulation. And playing the motion here is very difficult.
What is it? It's head. What is?
It's a LiDAR,
Uh,
rotating LiDAR to generate a 3D point cloud. So see, standing like this is very challenging to compute. This is something that I did about 30 years ago, walking in tunnels and maintaining balance and stability during the walking and programming the entire motion sequence. And okay, I'll continue slow. This is Boston Dynamics. Again, this is a relatively old movie. I think it's from 2014 or something like that. And they have a predefined gate pattern, but a reactive control. And reactive control can react to changing environment and also for external perturbations, external effects. So it's relatively old. You probably saw much more advanced movies. This was really the beginning of four-legged robot commercial, four-legged robots. Here it was not electrical, it was hydraulic in motors, and you hear the motor that compress the oil pump.
This robot is artificial intelligence or the program which
It's
or power or force to
now the question is, what is artificial intelligence? To program each movement with a reactive control and a predefined gate and adapt it to the terrain. This is kind of artificial intelligence, although it's not deep learning. It's everything that we do in this course, even graph search, is artificial intelligence.
yeah, the robot not to learn the surrounding.
This is something else. This is the machine learning is something else. Is not necessarily AI. AI is also the algorithms to solve the problem. But if you want something like machine learning to be able to improve itself and learn from its mistake, this is something else. And it's not this.
They don't use reinforcement learning.
Here they didn't do reinforcement learning. Maybe now they do a little bit. I'm sure they do.
Picking the robot.
It's reactive control. It's not.
Very impressive what which is in models since then, because they see spot walking, they're more like latest version.
Yes,
You don't steer the motors at all, you steer the steps of doing.
because they change from hydraulic motors to electric motors.
Yes, doing the next one, very quiet.
Yes, and the electrical motors are direct drive, so there is no gear, and therefore you don't hear the gear. And they are relatively big to provide high torque in low speed. But with direct drive, and they can also, you can sense the environment, you can sense the current, the back EMF, the current, and then identify how much torque the motor applies. And this is more advanced. Again, not the latest version, but one of them. There's also a video of this where they show how many times the robot fell and broke during trying to complete this task.
Work better than me.
Yeah. They fell many times and broke many times until this video was shot. But yes, it's impressive. One of the difference between academia and industry is that in academia it is enough that the robot will work one time. You show that it is possible to do it. In the industry, it's enough that the robot won't work one time, and then The industry will tell you, take your robot and go away. It must work every time. So here's two works that we did about quasi-static locomotion. So walking while the robot maintains stability all the time of legged robots. One is for four-legged robots, the second is for two-legged robots. And I'll show you how it works. I think we'll do this after the recess. I'll pause the recording. Okay, we'll continue. So now we discuss the motion planning of a four-legged robot as the beginning. We want to do something like this motion of those ibex. When they need to plan the motion of each leg in order not to fall. Here it's more dynamic. They also jump, but we are dealing with the problem of selecting each foot pad carefully in order to maintain balance and advance. So when we come to design the motion, so there are two types of locomotion. One is quasi-static, so the robot is stable at every time, every instance, and also we can slow down the scale of the time, and it will still work. On the other hand, there is the dynamic type of motion, where the robot uses its inertia, its dynamic, in order to conduct the motion, like jumping, running, falling, and so on. About gate generation, how to generate the gate pattern, the type of movement. There was work about periodic gate and non-periodic gate. Well, sometimes this is called free gate as well. And some kind of the continuity of the movement. So it may be discontinued. So we do one step, stop, then do the other, then move the body, then do another step. There is the continuously motion. So the robot does one step, and during this step also move the body, and then does the next step and also continue to move the body. And there is another option to do double step. So it moves the body while doing two steps and not only one. So it's something in between. So this is the type of motion that we did with a small robot that we built in the lab. As you can see it here, it does 1, 2 steps and then move the body, and so on.
Helps for stability, or
This helps with the stability, yes. You have to move the body, but it depends when you move the body. Okay, about the kinematics. Here we have 3 degrees of freedom for each leg. Pretty simple. There's the forward and inverse kinematics of the robot. A little bit about the electronics, the motors, the controllers, the radio link between the controller and the computer, and battery as well. Then the configuration space. What is the space where we plan the motion? So we have the configuration parameters Q, which holds the location of the center of gravity, X, Y, Z. And here, center of gravity X, Y, Z, and the angle of the body, roll pitch yaw, 3 angles of the body.
What is L?
L is leg.
It's leg.
Yes. So we have 4 legs, as you can see here. L is 4 legs, and for each leg we have 3 parameters, which is the location of the tip of the leg. So in total, we have 18 parameters here. 4 legs times 3 parameters, this is 12, and 16 parameters of the central body. It's 18 dimension. The movement of the central body can move in any direction, as you can see here, while solving the inverse kinematics. And the workspace of the body, of the central body, is this kind of shape that you can see here. And for each leg, we also have a workspace for each leg, which looks like a ball. This is the area that each leg can move in, each footpad.
What is I?
It's which leg?
Right?
Leg I. Leg I can be leg 1, leg 2, leg 3.
What is the
Here's the radius of the outer and inner radius of this kind of ball. This is the
ball is the workspace you can do it, right?
Yeah. It's circular. And also providing a model for the ground. It's a height map, as you can see here. And this is the logo of MATLAB. Now, the question is how to measure stability. What is good stability? What is bad stability? We said before that this is also equilibrium. It's not actual stability. So there are different ways. What first is called the static stability. So if this is the support polygon, and this is the center of mass, you don't see my mouth. If this is the support polygon, so those 4 points are where the robot touched the ground, And this point in the center here is yes, is the projection of the center of mass on the ground. Then there are different criterion for stability. One is the static stability margin. It means how much the center of mass is far from the support polygon. What is the closest point on the support polygon to the location of the center of mass?
Your desired value for the center of mass will be in the center of the area.
We want, in order to maintain balance, we need that the center of mass will be above the support polygon, not necessarily in the center,
Just inside.
just inside. It is enough. But if you are right on the boundary, every small motion will cause it to tip over. So this measure how much the center of mass is inside the polygon. And there is the longitudinal stability margin. It means the distance of the center of mass from the support polygon boundary in the direction of motion. And also CLSM is the crab longitudinal stability margin. It's in some certain direction margin.
What are we measuring? The distance?
The distance from the projection of the center of mass to the boundary of the support polygon.
So which method is just
In different directions. Yes, exactly. Well, SSM is actually the closest point because there is no priority for different direction. Another option is the energy stability margin. It means if the center of mass is above the support polygon, how much energy I need in order to lift this center of mass and rotate it around one of the edges of the support polygon in order to tip it over. So I need to put some energy to raise the center of mass and rotate it around the edge of, as you can see here. No? Yeah. If this is the edge of the center of the support polygon, and this is the center of mass, I don't want, but this is the measure. I need to raise the center of mass in order to move over this line, which is the boundary of the support polygon, and rotate it to tip it over. So I need to raise the center of mass, and this requires energy, and this measures how much energy I need in order to cause it to tip over. And there is another measure, the normalized energy stability margin. It's another version of the energy of the stability margin in order to tip it over. Another method or measure for stability is called feasible equilibrium region. This is work by Izar Or and Elon Rimon from Technion. And what they did is that they show, I'll explain this. They show that basically that the a support polygon is not enough in some cases. Sometimes the support polygon is smaller than the actual support polygon. So the idea is that this is the equilibrium equation. As you can see, where is my mouse? Yeah. As you can see here, this is the sum of forces on top, and bottom it's the sum of torque that is caused by the contact forces. And each contact force has to be within the friction cone. It means that this is the normal part of the contact force, and F minus the normal part is the tangential part. It's actually the friction force. This must be smaller than mu n, mu F dot n. And this is called friction cone because if I draw the tangential force and the normal force there, and I take the vector which is the contact force, it's the total between them, it's the sum of them. Just a second, I want to show you. Yeah, if I have the tangential force and the normal force, and the actual force is the sum of them, so it's something in the angle. And this force, if we have the constraint that it's the tangential force is smaller than mu n, then this causes something like a cone that the contact force can be in. And the angle of the cone is arctangent mu, the coefficient of friction. And you can see here the friction cone, so the force must be within this cone. And we can also estimate it with a kind of a pyramid. And the idea is that if the robot legs touch the ground, as you can see here, and if it touch such that the friction cone does not include the normal, the vertical line, actually, the normal, and the friction cone does not include the vertical. Yeah. No? Yeah. So you see the vertical line, and you see the normal to the contact, and the vertical line is not inside the friction cone. Then the support polygon, which here is this triangle, is reduced to this area, which is smaller than the actual support polygon.
When the vertical line actually here.
It's the direction of the gravity. The vertical line. Yeah. So now, when we have four-legged robots, we have 3 contact points. You see here, L1, 2, and 3. We have the support polygon, as you can see here. We have the feasibility equilibrium region, which is smaller than the support polygon. We have the center of mass and the places that we can move the body in order to move the center of mass. And we have also the workspace of the fourth leg, which is kind of lifted now in the air. And we must have the center of gravity above the feasible equilibrium region here, with some margin, as you can see here, in order not to be on the boundary. And then we can move the leg forward inside the this area. So the basic of this algorithm is that we check the possibilities to do double steps. So move one leg and then another leg, and then the central body. For each double step, we need to solve a 10 parameters minimization problem, where we want to minimize the effort here, U, such that we maintain equilibrium and all the legs are within their workspace. So we model the problem as a graph. A node of the graph is a specific posture, Q, is the set of parameters. A graph edge is a possible transition from one posture to another, so the ability to conduct step in order to move from one point to another. We use the DFS algorithm in order to advance in the graph. And we use a heuristic, which is kind of a cost function that we want to minimize. And it's sort of a potential function. So the cost function is combined of three different costs. One is to minimize the distance from the target, is actually the distance from the target. Second, there is the heading. We want the robot to walk towards the target, which is head first at the front. And another potential or another cost is the distance from the pre-planned path. And we may have some local minima problem. You can see here that for potential function, there is problem of local minima. This is the algorithm. I won't get into all the details, but you can see here some simulations of this robot walking and changing the position and also overcoming here a ditch there. And here is another thing that we have a place that the robot cannot move. And this is actually a local minimum. And it fills the local minimum until it finds a breaking point, the point to move out of this local minimum. And after post-processing, there is a waypoint in the middle. And this is kind of example of how it works. some kind of challenging terrain. As you can see here. The side view, and this is the actual motion.
Well, little lady, let me elucidate here. Bobby wants to be a cat, because a cat's the only cat. No,
This
where is
is,
that hell there? Bobody's picking up on that feline beat. Everything else
Walking
is
pretty
obsolete.
slow.
A square with a home makes you wish you weren't born.
The
Every
cat
time
was
you
not
play.
interested.
But with a square in the act, you can set music back to the caveman days. I've heard some corny birds who tried to sing.
Okay. Next is the locomotion of a humanoid robot, a two-legged robot, and we did something very similar to the previous one. So humanoids, there's many types. Again, we define a free gate, a gate that there is no gate pattern. So we generate it during walking. We are walking on three-dimensional terrain. There are some constraints. The kinematics is the reachability, how much the leg can move forward and backward and sideways, and also the stability, the equilibrium constraint. And for motion planning, we are doing graph search and potential function as heuristics. So we have a support polygon, but in order to move, we need to lift one leg, and therefore the robot needs to move its center of mass above the leg that is on the ground. This is the kinematics of the robot. It has 3 degrees of freedom in the hip, 1 in the knee, and 1 in the ankle, and 2 in the ankle. For inverse kinematics, we solve the inverse kinematics problem in a numerical method using the Jacobian, as you can see here.
Isn't it computationally expensive to take an inverse of the matrix?
Not so much. It depends how big is the matrix, but
And in the robotics, it's not too much. Like I had a course last semester with you, and he said that it's
it depends on the size of the matrix. Here's 6 by 6. You can do it numerically. So the idea of the algorithm is we start the position. We have the start position, the target, the map, and some tolerance to get near the target. We start with a step sequence, generate step sequence, and find if this is the distance of our path from the target. If not, we plan more, and this is very similar like before. For each step, we move the foot to some kind of a via point a waypoint in the middle, just to lift it and then move it to a point, rotate the pelvis in order to allow a larger workspace for the leg. We rotate the pelvis. This is what humans are doing, but elderly not so much, not turning their body. Move the foot to the goal and then move the pelvis forward to maintain the center of mass above the support polygon. This is the idea. Again, we're searching 2 steps forward, but conducting only 1 step. The second step provides the orientation of the first step. So since I'm planning ahead, I can provide what will be the orientation of after the completion of the first step in order to be ready to conduct the next step. Footstep selection algorithm calculate the potential of every second step, how far we are from the target, order the steps in ascending order, checking constraints of balance and reachability, select the first step that meets the constraints, and this is how it is done. This is what it actually checking the orientation and planning forward. You can see here. Oh, what happened? Yeah, this is for walking on flat surface. And this is walking on surface with kind of stairs. So there is an option to go over the stairs and walk directly. This is one kind of heuristics. And the other option is to go around, not to go so much. As you can see here, this is only 1 step because going another step is maybe will have cost, which is more.
How does it know the height of the surface?
This is provided,
Provides.
the algorithm. But usually it has a LiDAR to measure. And here is a little more complicated terrain. And you can see that the robot, for going in order to go forward, it turns backward. You see? And it wasn't pre-planned. This is a solution that the robot found. And this is because of the angle constraint in the ankle. So the robot cannot go forward and put the ankles up enough, and because it will fall backward. And therefore, since there is a larger angle to put the ankle down, therefore it chose to go backward, which is more stable. It's the same. Same thing.
It's really like human walking, right?
Yes. Similar, not the same. And here's the problem of local minimum. You see, the robot is planning, is going towards the obstacle and then move back because it cannot go through the obstacle and then go around. And this is, no. It's not an actual example, but it's 2013. Saying balance is difficult, as you can see here. By the way, to cause the robot to enter this car, this golf car, and plan the motion, how to do this is very challenging problem. Because the robot is big, the chair and the car is very small, so it's very challenging.
Also make it to drive.
Yes,
It's hard.
yes. That was part of the robotics challenge.
What changed in the 10 years from this last video to today?
A lot.
Besides computational power?
A lot. Computational power, algorithms, advanced simulation, much more advanced. And so the ability to plan the motion and react is much more. And now it's much more, it's much easier. So then Arduino was at the beginning, ROS was at the beginning. And so processing the LiDAR, the localization, the planning was, everything was just at the beginning. And now it's much more advanced.
Do you think about it?
Nice. Nice game. Yeah, that was my lab a few years ago, more than 10 years ago. And okay, I think we'll take the 10 minutes now, and we'll continue after that with the new chapter of the next chapter of the course, which will be the kinematic and then dynamics and control. Okay, we continue. The next part is a little review of a short review of the kinematics. First the background, then kinematics, and then we'll go to dynamics. And if you think you know this and this is And this is something that you know, we can skip this. So, a little bit about vectors. Vectors are column vectors. For two vectors, we have the scalar product, the inner product, which is A dot B, and we can write this in a matrix format as A transpose, which is a line vector, a row vector, times B, which is a column vector. So it's simply a way to write this in kind of a matrix form. And then we have the cross product, A cross B. Sometimes we write this as A cross, the matrix A cross, times the vector B. And the matrix A cross is simply this matrix. And when we multiply this matrix by B vector, a column vector, we get the cross product. Next, a little bit about rigid body transformations. So rotation matrix, rotation preserve the distance between points. So the rotation between a point, a location of point or a vector in one reference frame, it is transformed into the same vector in zero reference frame by multiplying the vector with a rotation matrix, where the rotation matrix is composed of the vector, the base vectors of the first reference frame as they appear in the zero reference frame. So this is the mapping R between the one reference frame to zero reference frame, as you can see here. And x10 is the vector x of frame 1 expressed in frame 0 components. And this is sometimes called the DCM, the direction cosine matrix. So the example here, the rotation matrix, if I have a rotation about the z-axis, as you can see here, two reference frames. The rotation about z-axis is actually this matrix, where the first column is the x-axis of the first reference frame expressed in zero reference frame. And here are the rotation matrices around all the axes. You see around Z axis, around Y, and around X. And some properties of the rotation matrix. So the inverse of the rotation matrix is actually the transpose of the matrix. And we can prove this by looking at R transpose, which is also similar to R transpose R, because this is actually the transpose of this, and this equals I. And if we take this we take R transpose R transpose is X transpose Y transpose Z transpose times X, Y, Z. We have the unity matrix. X transpose X is 1, X transpose Y is 0, and so on. The determinant of the rotation matrix is 1. This is easy to show. If we take the square of both sides, then square of 1 is 1. Determinant of R times the determinant of R is similar because determinant of A times B is determinant of A times the determinant of B, and therefore determinant of R times determinant of R is like the determinant of R transpose R. The determinant of R transpose is like the determinant of R, and determinant of AB is the determinant A times the determinant B. These are the two rules that we used here to show how we moved from here to here. And R transpose R is simply I. Determinant R transpose R is I, and determinant of I is 1. Also, determinant of R is X transpose dot Y cos Z. The rotation matrix properties are two things: is the special orthogonal matrix, where R is the rotation matrix, can be size n, can be either in 2-dimensional or 3-dimensional or n-dimensional, and it has the property that the transpose is the inverse and the determinant is +1. Rotation matrix is a rigid body transformation. And so RP minus RQ, this is after the transformation. This is the vector between P and Q after the transformation, and this is the vector between P and Q before the transformation. And the distance between P and Q is like this: RP minus RQ square here is RP minus Q if we take the R outside of the parenthesis here. And then we take the square, it's the vector times itself. So it's R times P minus Q multiplied by itself. And then we get, if we take the transpose here, then we change the order and we put the transpose of each matrix. And therefore we get R transpose R. Oh, you don't see my... Therefore we get R transpose R here, which are I. And therefore the distance is of this is like the distance of this, as you can see here. And it preserves, rotation matrix preserves the distance between 2 points on a rigid body. And if I want to take sequence of rotations, so I want to rotate first x1, then x2 by alpha and then beta. And therefore I take the rotation between 2 to 1 and multiply this by 1 to 0. and then this is the rotation from frame 2 to frame 0. You see, this is the first rotation, this is the second rotation. Because we did from 0 to 1 and then from 1 to 2. But if I want to rotate something around fixed axis, so I want to rotate around the x-axis of the global frame, of the world frame, then the rotation is done not from the left, not from the right to left, but from left to right. As you can see here, I take the first rotation from 1 to 0, then rotate around 0, then rotate back from 1 to 0, from 0 to 1, from 0 to 1, and then from 1 to 0, and this is the rotation from 2 to 0. So you see, R is the rotation around the fixed axis, and eventually this and this kind of disappear, and we get R times R10. And this is the second rotation, this is the first rotation, we just replace the order. If I want to rotate around a fixed axis. And a little bit about Euler angle, so we can represent the rotation, the orientation in different ways. So rotation matrix can be parameterized by 3 types of rotation. And we can choose what kind of rotations we want to parameterize. There are 3 angles. And so Euler said he wants them to be Z, Y, Z. Rotation around Z, then Y, then Z. Again, the new Z. And so those are Euler angles. Alpha about Z, beta about Y, the new one, and then gamma about Z, the new Z. And the rotation matrix is this. Another way to parameterize the rotation matrix is by 3 angles called roll, pitch, yaw, which are rotations around fixed axis, around the x and y and z of the global frame, the world frame. So phi about x-axis of the world frame, then theta about y-axis of the world frame, and then psi about z-axis of the world frame. But now we multiply in a backward order. So the first rotation is on the right, and then the second and third on the left. And those are all pitch yaw parameterization of the rotation map. Now, if I want to do both rotation and transformation, then I have a point here. I have a vector in the frame of the rigid body. So in order to express the location of this point, I need to add this vector D with the vector R, but they have to be in the same reference frame. So first I take the vector R and transform it from a reference frame 1 to reference frame 0 by multiplied by the rotation matrix, and then add the D translation vector, which is already expressed in 0 reference frame. And therefore, we get the the location of this point in the 0 reference frame. And now we can define the special Euclidean group SE, SE3, which is two parameters, D and R, where D is the translation vector and R is the rotation matrix, as you can see here. And in order to write this rigid body transformation in a matrix form, we can then convert it into a matrix multiplication, but by doing that. This is the rigid body transformation as we saw. And if we define a transformation matrix A, homogeneous transformation matrix A, with the rotation matrix here, the translation vector on the right, and then a row of 0 and 1, then when we multiply this by a vector in the 0 reference frame, we get exactly the rigid body transformation equation. The only thing is that we now have to have 1 on the bottom of each vector, of each point vector. And we can use this sequentially, one transformation after the other, as you can see here. And this is the first vector. If I might multiply it by the transformation matrix, I get the vector in reference frame 1, instead from 2 to 1, and again from 1 to 0. So if I want to transform points from reference frame 2 to 0, I do first 2 to 1, then 1 to 0, and simply multiplying the transformation matrix in this order in order to transform vectors from reference frame 2 to 0. So we said we have the position of a point on a rigid body, and it is according to the rigid body transformation, where R is in a local reference frame, 1, and D and R0 are in the global reference frame 0. Next, we want to get the velocity of this point on the rigid body. So in order to compute the velocity of this point on the rigid body, we need to take the derivative of the position. So we had the position of the point R. If we take the derivative, this is V, the velocity. And then we can, then we need to take the derivative of this as well. So R1, we said this is constant, it doesn't change because it's point on a rigid body. So R1 it does not change, but the rotation matrix and the translation vector can change over time because the object may move and rotate. So how we compute the R dot and D dot. So first, let's discuss the R dot. If we have R transpose is equal Y, then if we take the derivative of the two sides, on the left, we have a derivative of multiplication. So it's R dot R transpose plus R dot transpose. And this equals to the derivative of I, which is 0. We see here that we have R dot R transpose on the left. We take this to the right. And we take the transpose of everything. So the transpose of R dot R transpose is simply R transpose because we change the order and put transpose to each. So transpose is without transpose here. And the R dot becomes transpose. So we have the same matrix on the left and on the right, but on the right we have the minus transpose. Now the question is which matrix is similar to the minus transpose of itself. It's only very special type of matrix. And this type of matrix is called skew symmetric or sometimes also anti-symmetric. Because if the transpose equals to the to minus the original matrix, then items on the diagonal won't change in transpose, and the only number that equals to the minus of itself is 0. So it has zeros on the diagonal, and all the off diagonal parts are one minus the other. So you can see example here that A cross B, we said this is A cross B, the matrix A cross. And this matrix is also anti-symmetric or skew-symmetric matrix. As you can see here, there are diagonal, 0 on the diagonal, and you see AZ here and minus AZ here. So it's kind of the opposite paths on the diagonal. So this is also a skew-symmetric matrix, the A cross. So we can write this R dot R transpose as a skew-symmetric matrix. And we can call this matrix as omega cross. Omega cross, we call this the matrix R dot R transpose. And look at omega, we have 3 parameters. It's X, Y, Z, like here. And then if we define omega cross as R dot R transpose, we have here V equals R dot R plus D, but R dot is R dot R transpose is omega cross. So we can have omega cross, and we need to take off this R transpose, so we multiply by R again. If I multiply here with R, then R transpose R is I, and we left with R dot. So omega cross times R, this will be R dot. And this R1 and D1. So we take this and see what this is. This omega cross R1, 0, this R1 and when we multiply it by R10, this is actually R0. And this is omega cross R. Omega cross R is the tangential velocity due to rotation, as we know from dynamics, omega cross R. Plus D. D plus D dot. D dot is the relative velocity. It's the linear velocity due to translation. So if the whole body moves as a rigid body and not rotate, this is D dot. And omega cross is the amount of velocity that comes from rotation. Exactly as we saw in dynamics school. Yeah. Euler's rotation theorem. Euler rotation theorem states that in three-dimensional space, any displacement of a rigid body such that a point on the rigid body remains fixed is equivalent to a single rotation about some axis that runs through the fixed point. So Euler said that every rotation and translation of a rigid body, only rotation, sorry, not translation, that every rotation or set of rotations of rigid body can be expressed as a rotation on some axis in the space. So every rotation R, rotation matrix R, is equivalent to a single rotation about an axis W in angle theta. So only one rotation can represent any rotation matrix. Since R is an orthogonal matrix, it has eigenvalue 1. So eigenvalue 1, that means that RW equals lambda W, but lambda is 1. So R omega equals omega. And the question is which vector after I rotate it remains the same vector. This is the rotation the rotation direction, rotation axis. When I rotate through around some axis, the only vector that doesn't change is the rotation direction, rotation axis. And so the rotation axis, omega, is actually the eigenvector, which relates to the eigenvalue 1 of R.
This is only true for the Euler theorem, right?
No, that's true for every rotation matrix. That's good for every rotation matrix. If you want to know which is the rotation axis, simply take the eigenvector of the eigenvalue 1. And so it's a pretty strong theorem. The reason Euler here is because he found it.
No, there's also.
But it's not related to the Euler angles.
No, but. Because the Euler vector.
Yes, this is how you find it. Yeah. Okay. Let's continue. So next we discuss forward kinematics. If I have a robot with many links, what? if I have a robot with many links, as you can see here, for each link, I put a reference frame. And then if I want to know the location of a point on the end point of the robot, I simply need to transform it from the most lateral or external frame to the initial one. So I multiply this point, this vector, by a n minus from n to n minus 1, and then all the way to a2 to 1 and a1 to 0. And each transformation matrix, homogeneous transformation matrix here, depends only on one parameter, only on one angle of the joints. And we can see, we can do some example of a SCARA-like robot, as you can see the drawing on the right. And so the reference frames that we took at the beginning when angles are 0, all the reference frames are parallel to each other. And we take here the first reference frame, the world reference frame, and then this is the first one rotated about theta, about Z1, Z0, and then the second one is here rotated about Z2 by theta 2, and the last one is rotated by theta 3 around Z3, and here there is a translation of D4 from reference frame 3 to 4, the end effector, as you can see. So if we write all the transformation matrices, the first one is simply a rotation around z-axis, z0 by theta 1, so it's cosine and sine of theta 1, and the distance, the displacement between the first reference, the 0 reference frame to first, is simply h along z0, is h along z0. As you can see here, this is the 00h vector. Again, for the second transformation matrix, and we have the transformation from 1 to 2 by rotating of theta 2 around z1. So it's rotating by theta 2 cosine and sine of theta 2 around z-axis, z1 axis, and the translation between them is L1 along x1. So L1 along x1 here. And from 2 to 3, we have a rotation of theta 3 around Z2, theta 3 around Z2, and the translation of L2 along X2, L2 in X2. The last transformation is from 3 to 4, which is only translation, no rotation, So the rotation matrix is the unity matrix. And the displacement matrix, the translation matrix, is D4 along minus Z3. So you have D4 here, as you can see. And the total transformation matrix from 4 to 0 is simply the multiplication of all of them. The inverse kinematics is the opposite problem. Now we know where we want the end effector to be, the end of the robot, and we ask what should be the angles of the joints. There is no analytical, automatic way to find the analytic solution for this. Sometimes there is analytic solutions. Sometimes it's difficult to find the analytical solution. I'm not sure it's not exist, but it's difficult to find. And then we use numerical solution for the inverse kinematics problem. But we'll see here an example which is used in many cases for robotics arms. The use of kinematic equation to determine the motion of a robot to reach a desired position for a given position and orientation of the end effector. What should be the joint angle or displacement? So you see, if the end effector needs to draw this circle, what should be the angles of the joint? So we take first an example of 2 degrees of freedom robot with 2 angles, θ1 and θ2. And the location of the end effector, the end of the robot, is simply L1 cosine θ1, this is this distance, and then L2 cosine θ1 and θ3, θ2, which is this distance, and this gives us the x-axis position of the end effector. And similar with the sinus, with the sine to the y-axis. And now the question is, for a given xy of the end effector, what should be θ1 and θ2? And how we find it? So this is the drawing. And we do something like this. First, we look at, we know x and y, and we want to know what are q1 and q2, or θ1 and θ2. So we draw this triangle from the origin to the end effector. And the end effector x and y, we know the position. So the length of this part of the triangle, we know. It's simply Pythagoras theorem. As you can see here, r squared is equal to x squared plus y squared. Then we look at this triangle and we use the cosine theorem. And according to the cosine theorem, we have r squared on the left and plus the square of these 2 other sides of the triangle, which are a1 and a2. a1 square plus a2 square minus 2 times a1, a2 cosine the angle between them, alpha. as you can see here. So we can compute what is cosine alpha. Cosine alpha is simply we move those to the left and divide by 2 a1 a2. So this is the actual term of cosine alpha. And Q2 is simply alpha pi minus alpha, as you can see here. So cosine Q2, because of the pi, is minus cosine alpha. So we have cosine alpha here, and cosine Q2 is minus this. So it's x squared plus y squared minus a1 squared minus a2 squared divided by 2a1 a2. And this allows us to compute cosine Q2. So now we have Q2. We have cosine Q2, and we can say that the sine of Q2 is the square root of 1 minus cosine squared. Because sine squared plus cosine squared is 1. So we have the sine as well. And since we have a sine and cosine, okay, we're still left with this. And now we look at beta, which is another angle, and we look at the red triangle here. In the red triangle, we already have Q2. So this is actually, this part is A2 cosine Q2. We have A2, this is A2. We have cosine Q2, and this is A2 sine Q2, so we have this as well. So the whole distance here is A1 plus A2 cosine Q2. This will be this. And this is A2 sine Q2. So beta will be the arctangents of the sine divided by the cosine here, as you can see here. So we can find beta. If we have beta, then you see from this big red triangle, we can find what is gamma actually is the tangents of y over x, the arctangents of y over x. And then Q1 would be gamma minus beta. And beta we already computed here. So this is Q1. And Q2 we found before as cosine Q2 and sine Q2. So we can do also arctangents of Q2. Yeah. So those are the two equations. And this was the geometry trick that we used in order to find the inverse kinematics. So now that we have x and y, we can find Q2 and Q1, as you can see. And if I want to draw a circle, I simply put the x and y of the circle, and then compute the Q1 and Q2 for every point along the circle. And we found this analytically. And this is very useful for many types of robot, including the SCARA robot, as you can see here. It's the same two links on top. So we can do this, use the same method for other robots as well. And that's it, I think, for today. We'll meet again next week, as usual.